Hi, this is the first video in a series I will call Logic in Computation. We may begin by discussing what is a concept called propositional logic. Also known as propositional calculus. It is nothing more than having some predefined terms, let's say A, B, and C, and let's give it some symbols like plus, intersection, and bitwise, or it could be any sort of symbol, you know, like an and, I don't know, a sigma. And what we do is, right, in propositional logic, we can combine these symbols in a vocabulary. So let's say for vocabulary 1, we have the terms plus intersection, a bitwise or an and a sigma. With this vocabulary, we can define statements. And this takes us to the definition of propositional calculus, or propositional logic, which is the creation of statements by combining terms and defining operations which interact with these terms in order to also become statements. So terms in of themselves can be statements, and operations can be statements as well, but they can be combined with terms to become statements. So let's take a quick break here. What is a statement exactly? Well, by the logic we were following, a statement is a combination of any sequence of terms plus any operations that we define. So the terms we defined on our vocabulary, let's say the first one, let's say A, we want to use it in conjunction with B and a symbol like epsilon, and we want to use these to do something, right? To do something that expands their original meaning, which is very void of significance. In other words, we want to use simpler bits of information to form bigger, more complex statements that do something bigger than the simple aggregation of themselves. Let's say they have some specified behavior when interacting with each other through certain operations that we give them. And by then they will become these statements that do stuff that is interesting and very useful in not just computation but logic, which is multidimensional in so many fields. And in return, at the end of this episode, we will have certain new notions of operations, operators, and statements, aggregations, which can be utilized in furthering our knowledge in logic of first order, which can then be expanded into the theory of computation. And from there on, we can explore stuff like computability and computational complexity, which is refining computability to know that problems can be resolved with certain resources, they're given memory, time, etc., limitations. So that's where we're gonna end in. But first we have to discuss the simpler, more abstract branches of logic. Okay, let's backtrack a bit. Let's talk about the vocabulary, right? We talked about it a while ago. And let's say we have some symbol, for example, sigma. Let's call that our vocabulary. And let's define on its interior, let's say it contains the symbols 1, 2, plus 3, and x. Yeah, let's say that's enough. Okay, now each of these terms, right, they can be joined together to form words. For example, 1, 2 plus 3 together, no characters in between, or let's say 2, 3 plus, all of them are words. So these terms together, they form words. And these words are constructed from the vocabulary sigma. Let's give another example. So like really quickly, let's say we have another vocabulary. Let's say we have the L vocabulary, and it contains all of the previous elements or terms of sigma, and this is how it is denoted with the asterisk. And this equal sign gives us an indication that it is the exact quantity, the exact amount. So nothing more, nothing less. It's a complete copy of everything that is contained in the vocabulary of sigma. So L is equal to all of what is inside sigma. They both here, L and sigma, they act as, let's say, containers. They're not really they're not expressions that you can evaluate to be equal to one another, because they don't represent the same entity. They represent copy, like L represents a copy of epsilon. It does not represent epsilon. So while it may have the same elements as epsilon, it is not the same as epsilon. It's like saying we had epsilon with all its terms, 1, 2, etc. And then we have L that obtains all of those, right? But they're copies, they're not the original, so they have the same designations, 1, 2, etc. But in a physical world, they are different. They're different entities, different elements. They have the same aspect. It's like cloning them. They're two entities. Like this is one eye and this is one eye, and this is 2J and this is 1J. So if you take those away, they don't look identical, but nevertheless they're different. So moving on.